Good afternoon, I'm Brett Ruffle, editor of Canadian Poultry. Thank you for joining us for this webinar on the importance of ventilation in poultry and egg production. Ventilation serves many purposes. It supplies fresh air, which is essential. It removes excess heat, moisture, dust, and odors from the barn. And when properly designed, winter systems also conserve energy. Joining us to discuss this important topic is Ross Demerly, engineering sales manager at Munters. Ross has designed ventilation systems all over the world. He is also one of the inventors of Munters Drive technology, which is used in their high-efficiency fans. And joining Ross is Adam Pohl, project manager at Ruby 360. We encourage you to submit questions throughout the webinar. Ross and Adam will be happy to answer them following the presentation. And please note that a recording of this webinar will be emailed 24 hours after the live event. Now I'll pass it over to Ross to get us started.
Thank you, Brett. I am Ross Demerly, and today we're going to talk a little bit about the importance of ventilation. And as Brett said, today with me is Adam Pohl, project manager at Ruby. With nothing further, let's get started. So topics for discussion in terms of what we're going to discuss today. Talk a little bit about the definition of ventilation and how we look at ventilation. Some properties of air, and we'll get in, talk a little bit about minimum ventilation, jump into summer ventilation, types of building ventilation, and then we get into discussion of high efficient motors, as well as how do we run those motors with the control staging. So ventilation as defined is the proper movement of air through a building to replace the stale air inside the building with fresh air outside. And one of the objectives is that we need to make sure that we can replace that air without causing stress on the animal. Now, stresses here can be such as too cold, too wet, too much ammonia, too hot, and many other items as producers or growers that you would know as well. So what is our key objectives? As we mentioned, to remove and control moisture, to remove the CO2, provide fresh oxygen for the animals, and then in summer to remove the heat buildup either by the animals or the birds, promote growth, and lower the mortality. So as we get into minimum ventilation here, how do we do that? What's involved, and why do we ventilate? One of the keys here for minimum ventilation is to ventilate to control moisture. And as we can see here, we typically, and I think the industry looks at trying to maintain somewhere in the 40 to 60% RH range. And then with minimum ventilation, typically we will have some form of air inlet. And so we need to make sure that those are set uniformly so that we maintain uniform air flow in the building. We will add heat if needed to maintain the desired temperature, maintain sanitation to control ammonia. Now, sanitation can be anything from running your manure belts to cleaning the fans. I know maintenance becomes an issue that sometimes can get overlooked, especially as these animals are in the buildings for a longer period of time. And from a ventilation standpoint, we are going to look at a low volume airflow of about 0.25, quarter to a third of a CFM per bird. And I know there's some room around that for discussion. A little bit on properties of air. As you can see here, a 20-degree rise in temperature will double the moisture holding capacity of the air. And you say, well, yeah, why is that important? Well, we'll get into that here in a little bit as we talk about the buildings themselves. One key note here is every gallon of water evaporated will remove 8,700 BTUs of heat. So that's how much heat energy is going to be required to evaporate that gallon, which in the summertime, if you're going to use evaporative cooling systems, that's good, or foggers or something. But in the wintertime, we need to be careful as to if we have our drinker system that's got some nipples or something that's leaking, that water's going to leak out. Well, in order to maintain the building, we need to evaporate that water, and that's going to pull heat from somewhere. And typically it's going to pull it from the birds. So we just need to be careful of that. And a few more properties, maybe some rules of thumb. I think some of these you will be very familiar with. Cold air falls and warm air rises. I think that one's pretty common. As velocity increases, and this is referring to mainly like out of an inlet, the cold air stays up longer. The turbulence or friction that the air encounters as it spreads across the ceiling or down through the cages decreases the velocity, but then also increases the friction and the static pressure. And warm air can hold more moisture than cold air. As the static pressure increases through an inlet, so as you're bringing air into the building, how much do I need to open my inlet? What pressures will I be seeing? And what's the airspeed through the inlet? The general rule, as you see here, a 0.05 pressure should equate to roughly about 800 feet per minute through your inlet, and 1/10 of an inch is going to run you about 1,100 feet per minute. So as we look at building ventilation and the velocity, I said earlier, as the velocity increases, the cold air stays up longer. So as we are working in what can be some very cold climates, we need to make sure that we can keep our pressure so that we don't have that cold air dropping too quickly. Now, one of the issues that occurs is as the static pressure increases, so we try to pull a higher pressure to keep that velocity, the fan efficiency is going to decrease because the fan is looking at it as how much work do I have to do to move this amount of air. And so the fan is going to say, well, the higher the pressure, the less air I can move. And one of the keys to remember is a fan is like a pump. Okay, it's like a water pump. It is going to move a given volume of air from the building. That air is going to come from somewhere, and so we want to make sure that that air is going to come through the planned inlets of where we want the air to come through, and not through other areas, cracks, and doors open and things like that. So as we jump into this and we get into what is minimum ventilation and what are the components to make a good minimum ventilation system. As you can see here in this picture, the components as listed here, you have the inlets. The inlets here happen to be a bi-flow ceiling inlet. Then you have sidewall fans. And in this picture, we're looking at circulation fans. So here we have some circulation fans, which is can be a vital part of our minimum ventilation system to make sure that we get proper air distribution in the building. And then to tie that all together and to make sure everything's operating properly and we're running the right speeds and not over-ventilating or under-ventilating, we need a good control system to operate the building. So this would be a similar building as to the previous one. This time you can see that the building is populated with birds. You can see the inlets that are open. The circ fans are running, and we have a good uniformity of birds spread out through the building, which is a good indication that our inlets are set correctly. We're mixing the air well. We have some uniform temperature, so the birds are not trying to move all around or congregate in certain areas. As they congregate, as we'll get into a little later, that can cause all kinds of other issues for maintaining a good environment in the building. Minimum ventilation when it comes to cold weather. One of the things you'll see here in this picture is we have some sidewall inlets, and it is cold out in this particular building. This would be in the, I guess it's in the Dakotas, just outside of Canada, I believe. So it's in a very cold region. I think you can see on like the third inlet down here, you might see a little frost build up on one of the flaps of the inlet. So the one thing we got to make sure is, as we look at an inlet system, what makes a good inlet? Well, the inlet needs to be designed for your climate. So there are a plethora of inlets on the market, and some work considerably better than others for the really cold climates so that they don't freeze up. An inlet that freezes up isn't going to do you a whole lot of good. And then one of the things we want to make sure of as we're walking the buildings and we're looking at our minimum ventilation is to check the litter on manure belts, or in this case on the floor, for signs of high moisture levels. One thing that happens is, I'll get a call from guys saying, my floor is all slicked over. I noticed it today. I turned my ventilation up, but it's not doing anything. Well, the problem you run into here is it takes a while for the floor and for your manure to get wet, or the litter to slick over. That normally doesn't happen in just a short period of time. That's something that occurs over time from the fact that we are underventilating our particular buildings. So what does all this mean to us on minimum ventilation? Well, the goal here is to take the cold air from outside, bring it in, and mix it with the heat in the building, or either from the chickens or from additional heaters. And then, as you see, as we talked about the properties of air, that same air molecule now has expanded because it's warmed up. And the amount of moisture it can hold now is greater. So now we want to take that air, pass it through the animals and across the litter, pick up the moisture and the gases, and then exhaust that air out the building. And that's, in its simplest form, kind of what our goal here is in minimum ventilation. This particular slide here, I guess, kind of put this in here maybe to give you guys a little bit of humor as we start talking about summer ventilation. But yet here the building's a little surrounded with snow yet. It gets tough to really think about summer ventilation as we still have snow on the ground in areas. But summer ventilation becomes a very key component of building design. And so we will launch into that. So as we talked about minimum ventilation, we're going to talk a little bit about summer ventilation and what our key objectives are here for summer ventilation. We need to ventilate to remove the heat produced by the animals. Again, we need to set our air inlets for even distribution. Need to add cooling to reduce ambient air temperature, provide a source of air velocity, and a lot of the buildings, you know, when it comes to the layers, should be in the 5 to 7 CFM per bird range. Now I know and this is maybe more for a cage system, as we move to aviaries or we move to cage-free systems, those numbers may vary a little bit. So let's talk a little bit about how do we design a house and what do we need to do. Well, the first thing we need to do here is we need to remove heat from a house. So we need to provide adequate air exchange for the heat and moisture removal. So again, this isn't necessarily talking about the velocity in the house yet. This is mainly talking about there are so many BTUs in the house that's either from the ceiling, from the sidewalls, from the birds, but we need to be able to exchange that air and remove the heat. Birds are also respiring, so we need to make sure to remove the moisture. So we need a good system to do that. Now the birds themselves, the birds are going to give off heat in 3 forms. You're going to get conduction when the birds, either through their feet or as they lay down, they're going to be giving off heat from their bodies. Radiating heat, and the main one that we typically deal with here will be convection, giving heat off to the airflow moving across their body. One of the things that to keep in mind here is as we talk about velocity over the birds, and some guys will say, well, if I just increase my velocity, I don't need to worry about adding any type of cooling to the building. Well, that's not necessarily true, because as we all know, the internal body temperature of the chicken, around 104 degrees Fahrenheit. As an outside temperature starts to approach that, and you're blowing air across the animal, there's no temperature difference anymore, and it gets really difficult to remove heat from the bird. There's not much heat transfer that's occurring anymore. And so to maximize the cooling effect of the airflow, we need to make sure the air temperature is able to maintain below the body temperature of the bird itself. And typically, the way that's normally done is through use of evaporative cooling systems. And here, here's a picture. This happens to be a pretty large complex. But evaporative cooling is typically used. I know in other areas you will see foggers that are used instead of evaporative cooling. But the key item here is to make sure that you understand that if temperature is going to get extremely hot, depending on what area, your particular climate, we may need to make provisions for some form of cooling. So as we look at designing a system for the summer, where does the heat come from? All right. Well, this is a chart here showing you on a typical calculation of a good design, a properly insulated building. You'll see that, the birds are going to contribute 80% of the heat gain in that building. So as we look at, okay, where do we spend our money, for heat removal, you can see that a lot more involved with the birds. A little bit of where that heat's going to come from. 1 pound of feed is 1,500 kilocalories of energy, which is 6,000 BTUs of energy. In retrospective, a gallon of gasoline, so petrol, is 92,000 BTUs of energy. Well, how does that pertain to the bird? Well, as that bird digests the feed, it's typically going to put off about 12 BTUs per pound. And how that's split up is you're going to see 5 BTUs per pound is lost to the air through the heat transfer off their feathers. And then 7 BTUs is lost through panting. And what that's going to do is that's going to increase our relative humidity in the building, which is part of the moisture that we need to remove in the summertime as well. So as you can see here, just a simple math calculation, if you have 50,000 birds in the building and each bird is putting out 12 BTUs per pound with an average of 4 pounds, you're going to end up with 2.4 million BTUs an hour that you get to remove out of that particular building. So that's, again, should equate to roughly 80% of the heat you need to remove out of the building. Well, one of the nice things that we're able to do with ventilation is we can help this heat removal and the effective temperature of the bird by producing wind chill. And we're going to produce that wind chill by creating a velocity in the building, creating a velocity over the bird. And there's been multiple different studies done on what the temperature velocity profile looks like for wind chill. This is one particular graph that I like to use in regards to a quick reference wind chill effect. So if you look here, and we're down in the 200 feet per minute, 1 meter per second range, you're going to roughly be 2 degrees of temperature drop. Where if you increase to 350 feet a minute, now you're more like 5.5 degrees of cooling. And as you go up the scale, your temperature, the effective temperature the bird feels is going to get better. Now, what does that look like? Well, if you have an air temperature around 90 degrees, depending on what the velocity that you're able to produce around that bird, you'll see the actual effective temperature the bird believes it is, somewhere in the 88 to 72 range, depending on what the bird is, where the bird's at and what velocity you're pulling in the building. Now from here, we've kind of talked a little bit about what minimum ventilation is and what summer ventilation is. Well, next let's talk a little bit about the types of buildings themselves and how do we produce the environment that we've talked about that we need for the animal. Well, in this particular case, I've kind of chosen, there's 3 main styles of buildings that tend to be built now. One is a cross ventilation or standard ventilation system, as we would call it. The other is a tunnel ventilation. And the third, newer style, I guess, is a cross ventilation in combination with tunnel ventilation that we will talk about. So conventional or cross ventilation system here tends to consist of a series of sidewall fans in the building. In this particular building, you'll see that you have both a smaller fan for minimum ventilation, in this case a 36-inch fan, and then you have larger fans next to it in the wall, which here are 51-inch fans. And so all of our ventilation exhaust is going to come out through the side of the building itself. What that looks like from a cross-section standpoint is, and again, depending on the type of building you have, this happens to be a design of a what was popular, a high-density cage house here, where the air is brought in under the eaves and then brought up into the attic, and it'll be brought down through inlets, and then air will be pulled down through and then through the cages and out through the fans. Now, one may ask here about, you may notice in this particular view, the air inlets are positioned over the cages. And I know that's a bit of a conversation that normally happens is, do I place my inlets over the cages or do I place them over the walkways? Well, in this particular case here, we have a insulated inlet that handles cold weather pretty well without condensating. And from a ventilation standpoint, with the stacked cages like this, we would like our air to come in and meet, the two air streams meet over the walkway, come together and come down the walkway instead of meeting over top of a cage and maybe dumping that cold air directly on the top couple cages. So in this particular design, we would prefer the inlet over the cage. With that being said, here's an example in this particular area where the number of rows and spacing work out to where we can position the biflow inlets over a walkway. So minimum ventilation here through the ceiling will be done with the inlets over top of the walkway. Now in the upper right hand corner over here, you will see that this particular building has the sidewall vents, which hinge at the bottom and open at the top here, which allow air to come out across the ceiling. And that works very well for the minimum ventilation. But the one thing I wanted to point out in this particular picture here is you'll notice there's some large doors, insulated doors below those inlets. And so in this particular cross ventilation, where all the air is going to come in, we're going to bring some of that air in the winter and year round over the top and over the cages. But then in the summertime, we're going to open this bottom door, and it hinges at the top and opens at the bottom here, and it's going to shoot air down onto the floor and then across the bottom section of the birds, so that we try to get more uniform airflow in the building for both minimum ventilation and summer ventilation. And the third picture here just happens to be a picture of some hoods over the inlets and some sidewall fans to just give you an idea of what some of these cross-ventilated, and or if you're in a high wind condition, put some hoods on, or if you're maybe looking to do some dark out over your inlets as well, you can put some hoods on and then put some dark out in the bottom of the hood. So that's kind of the cross ventilation. Now as we get into our tunnel, and tunnel ventilation we can do with or without cooling, depending on where where in particular your buildings are. For a tunnel ventilation system, most of you know that the large summer fans are positioned on the end walls or maybe wrapped around on the side wall as well on one end, and then on the opposite end you will have some form of an inlet or tunnel door to allow you to close them in the winter, but then to open them for summertime. Tunnel ventilation, as we'll talk about later, is a very good summertime ventilation system. Just some examples of some tunnel ventilation system, whether it is in a single story house or whether it's in more of a, this one happens to be in more of a high-rise building with a manure pit underneath. You can do them in, we can tunnel ventilate in either case. Next here, if you happen to get into a fairly large building, whether it's these high density houses or not, you will see buildings where tunnel fans are stacked one above the other to get enough fans in the building to create the velocity and heat removal that we need for the number of birds that are in there. One of the other things in these systems in tunnel, same as in the cross vent systems, circulation fans, we may need to have some of those to assist, at least in the center aisles, if not in the all aisles, to help in the winter for airflow and air movement and destratification in the winter time. So then the next system we're going to look at is what I would call the newer systems, which are cross with tunnel. So in this particular one, we will have sidewall fans down the sides and on the ends, as well as maybe using some of the tunnel fans for transitional ventilation as well. This particular one, it is a 3-floor, but there's 50,000 birds per floor. So here we're going to run, ventilation, and the further north we are here, typically we may run a third of the ventilation through sidewall fans, and then the rest of the ventilation in tunnel fans. Another example here would be a double wide house where we have a central corridor of air down the middle to bring in our air. But the key here is we have our sidewall fans for our minimum ventilation for cross, and then we have our end wall tunnel fans. And what that looks like in a cross section is here. So we're going to be bringing our air in from outside through inlets here, and then we have this air chamber between the rooms where we bring air out of the attic into this air chamber. And airflow wise, what that looks like is we're going to bring outside air in from the outside under the eaves, as well as into the attic, and then we'll come down from the attic into this air chamber, and then through our sidewall vents here, we'll bring air into the room, and then we can get our proper air mixing by doing that. And that seems to be a nice workable solution for the cross ventilation for minimum airflow. The other thing you'll see here is in these more open buildings without the cage-free and aviary, there will be some form of circulation fans. In this particular case, it's a 2-floor building, and each floor we're running a 36-inch Vario fan for circulation purposes. Pros and cons of cross ventilation. It is probably one of the best wintertime ventilation systems. We do have total control over the air changes. It does reduce dead spots in the houses during the wintertime. And house orientation is not necessarily as critical. Now, the cons, though, on the other hand, house orientation may not be, but as we have fans all on one side, we may need a little more space between our houses to not interfere with airflow out of that side of the building for fans. Depending on how the inlets are set up, you may not have the air speeds that we're looking for summertime wind chill. And we also may get some heat buildups in spots in the walkways in the summertime. It is a good summertime ventilation system, but as we look at the next slide here, the pros and cons of tunnel is a better summertime ventilation system. It allows us to be able to pull the air down the walkways and move the air through better. And again, you know, some of the same pros. Now with this one, we can space houses maybe a little closer if we need to and not interfere with the airflow. We don't have as much airflow coming out the side of the building. The cons, it is not the best wintertime system. If you use this just as a tunnel system, you tend to get lots of end-to-end temperature differences by doing this. And we can create some chilled and dead spots in the wintertime. So it really needs to have some sidewall fans for minimum ventilation. So the next thing I want to get into here is the applications using the Munters Drive brushless DC motor. In this particular case here, I'm going to talk mainly about the Munters Drive and using the Munters Drive mainly in my presentation. But most of these comments will apply to many of the other high efficient DC motors that are now starting to come on to the market itself. But Munters kind of was the first one who had come up with this type of a design motor for use. Currently, I mean, we're using this design in most all of the livestocks, whether it's broilers or layers or dairies. The Munters Drive is a product that's being used throughout the industry. What are some of the benefits of the Munters Drive? Well, we had this particular study that was done on a broiler farm in Italy, where they just wanted to take and use for minimum ventilation purposes only, not for year-round ventilation. Here you'll see the results. Power consumption after 55 days, the one flock was down 25%. The heater usage itself was down 7%. And then we had some good benefits on the feed conversion with a 5% reduction in feed conversion. What is the Munters Drive? The Munters Drive is a direct drive motor designed to operate. Now, as a DC motor, it cannot be just a motor by itself, but it needs a drive and inverter inside that will convert the AC into DC and send out the commutations to the motor itself. The motor, DC type motor, does have a higher efficiency than your AC motors. And being a direct drive motor, it does lead to lower maintenance with the lack of belts and bearings to change belt tensioners, grease, and so forth. The fan, this just happens to be a picture of conversion of a belt drive fan over to a Munters Drive fan. We do have conversion kits. One of the best things about the Munters Drive itself is it allows you to have a true variable speed big fan. And what that looks like here is, it allows for a smooth ventilation. So we have a nice curve here from its minimum up to its maximum airflow. Nice smooth curve that we're able to utilize then. So where some of the benefits come from? Well, as we slow the thing down, you'll see that we have a 70% reduction in power usage, but that's only equates to a 50% reduction in actual airflow. So the fan is more efficient as you slow it down. It also helps to reduce the negative effects of cycle. If you happen to run fans on a cycle timer, all the cable wear and tear with your inlets opening and closing, actuators and pulleys and so forth, it allows us to move away from that. Another case study here, we had some buildings that were done. This one happens to be a large integrator in Australia that we did a control setup here. And the key here, I guess, is just to look at, we put in percentages of operation for the fans. This is the CFM out of the Munters Drive. This was the original CFM using timer fans, belt drive. We anticipated the annual consumption. We looked at what the belt drive should give us from a watts per stage. We looked at what the Munters Drive should give us, and then we anticipated that we should come up with about a 31% savings in energy. Now, what did that look like in the field? These are actual results at the farm with consumption. I know it might get a little hard to see. I'll show you in the next slide here. The actual test results, the daily power consumptions. The blue here is the belt drive house, and the gray lines here is the Munters Drive. And you can see over the course of the flock the difference in energy savings that was done. And this was a test that they had set up and operated, and this was what they come. That chart I said was a little hard to read. This is a summation of that. And so what they actually measured was a 32% savings over the flock. One of the things we're doing right now is we have some test farms in with the University of Georgia, and preliminary results here are showing in a broiler facility. This one is showing about a 25% savings. But now that we've got it set up, Mike Zark believes he can tweak some of the settings now and be able to probably get closer to a 27% to maybe 30% savings. Just another way of showing that data. And here's basically just some hourly data showing the tunnel fans, the variable tunnel fans versus the on-off fans. And you can see, the dark blue tends to be a lot lower than the green. So we are able to reduce the power. One of the things from a generator and standby setup is you have a minimal spike when you start up the motor. Typical AC motor has a 4 to 5 time startup amperage draw, which then affects like your standby generators and the sizing that you have to put in to be able to handle that. One of the other benefits of Munters Drive itself is a longer life of the motor itself. This particular site happens to be a site layer facility in Brazil that we did. We used a fluoro camera and took some pictures of the Munters Drive as well as a belt drive fans. And here you can get an idea of the temperature. And as we all know, the heat in a motor is from friction losses in the motor itself. And the heat is typically what will take out the motors, the bearings fail and so forth. So here we have a nice reduction in temperature from an AC motor of 50 to a Munters Drive running 34.7 degrees. The motor itself is a pretty simple design. One of the keys I wanted to mention here is the fact that we have a bearing it's a sealed bearing on the hub, but it is buried, it's inside the motor itself here, so it is nicely protected against the elements that we all face in our buildings. A little bit of installation. One of the things that you can do and that we've seen by installing these motors is reduction in contactor and thermal overloading, because the motor has some of that built in. You don't need as much. The other thing is the motor tends to qualify for rebates or electrical efficiency incentives that are available on the market. One of the things you really need, though, to really be able to get the maximum benefit out of any of these motors is a good control system that will take and maximize the benefit of the fans and the motors. So as we get into here, some staging. This particular has, I think, 18 fans that we're running. It's a 2-room, so you see 2 particular buildings. So as I mentioned, staging and variable operations, one of the things that these allow you to do is you really get to start thinking more about your ventilation and how we operate. And in this particular building here, we're going to start out with some fans. We're going to start out with 3 fans, 336s, and we're going to operate them on variable speed over the first levels. We're going to leave them run 100%, and then we're going to kick on the next set of fans, but we're going to bring them on at a 50% value, and we'll speed them up. But we don't take them to 100%. We bring them to about 80, and then we turn the next group on at 50%, and we speed them up, and then the next group. And so we really don't turn any of those on full speed, the bigger fans, the 51-inch fans, until we get all the fans on. Then we start speeding them up together, 50, 65, 80, 100, so that we can try to stay in more of that sweet spot for the efficiency levels. Another example of some fan staging. This one happens to have both some belt drive fans for summertime, as well as some Munters Drive fans. So we have 7 24-inch continuous fans that are running. Then we're going to kick on 3 fans. Well, we're actually going to kick on 2 fans, and we're going to run them at 50% and then 80%. And in this case, we're going to take them to 100, and then we bring on 3 more fans, and then we slow them, all fans down to 30, and then we speed them all up. So what you can do here is, with your control system and having a good control, you can speed up and slow down your fans and create quite a ventilation table to give you a very nice linear ventilation system. And just another example here, I won't spend a lot of time on, but it's just another example of how we can change our fan staging layout, get more fans on at a lower speed, draw in more even uniform air in the building, and save energy while we're doing that. Just in summary, just a couple points here. The robust design of the motor itself was set up to be used in our actual operation for agricultural buildings. It is set up as a direct drive to be able to handle the torque that's required to operate these propellers in our environment and against the winds and so forth. And again, the control system, make sure your control system is able to take benefit of all the opportunities with the fan itself. And with that, I will turn this over to Adam and Brett.
Yeah, thanks a lot, Ross, for all of that. I just want to touch on the controls and staging, that it's really important to keep that in mind when you're buying a high efficient fan system, that you stage it properly to really take advantage of those fans. Yeah.
Okay, we got a bit of time for some questions now. We got a few in. So one is, are there any differences between fogging and evaporative cooling pads?
Yes, the main difference, an evaporative cooling pad typically is in the range 65 to 70% efficient, where a fogging system normally is about a 50% efficient.
Just to touch on that too, Ross, we typically don't see cooling systems and things like that up north. Where do you typically see those applications?
Quite a few of them we will see in, of course, a bit of the warmer climates. So starting, here in the States, in the Midwest and further south. And then as we go both to the east or west sides, we see quite a few of the buildings that will utilize in any of the areas where, 95, 98 degrees, you can maintain for a bit longer periods during the day.
Okay, we got another one in. Does the fan height on the side walls make a difference?
What's that again? The fan placement?
Does the fan height on the side walls make a difference?
On a single-story facility, it does not. If you have a 2 or 3-story facility, it does, because it does play into being able to get that air through the cage areas. So in a single-story house, we typically, through the studies we've seen, we haven't seen a large benefit. One of the things, a fan, normally we will try to have the fan in the sidewall, maybe midpoint of the wall.
Okay, and we got another one is, which is more important, the fan or inlet placement?
Well, that's a good question. That tends to be more of a question of the inlet itself. I think we're getting some echoing that's occurring. The inlet placement itself is by far the more critical. As we look at uniformity in the building and wanting to get that air coming in uniform across, we want to make sure that our inlets are placed accordingly. air moves towards a fan. I guess I would say, air is not necessarily the intelligence. It knows it's being pulled in a direction which is towards a fan. Now that fan, whether it's in the sidewall or end wall, that air is going to tend to just move slowly that direction, as opposed to coming in the inlet and having the velocity we want to mix that air properly.
Okay, and another one is, so what distance in front of the fan can I put a feed bin or something without affecting the fan?
Again, another good question. Normally the rule of thumb that we tend to go by is, we would like it 2 to 3 times the diameter of the fan. So if you have a 36-inch fan, 2 times 36, 72 inches, 6 foot away. As you go to a larger fan, like a 51-inch fan, the 2 to 3 rule is going to get you 8.5 to 12 feet apart. Now, in a perfect world, we would like at least 5 times the diameter, but we know that that's not really the case. We can't normally get that. So normally 2 to 3 times the diameter.
Okay, and one last question that came in. So if I flow the Munters Drive down too low, will it cause problems?
The short answer is no. You can run the Munters Drive really slow. I mean, you can turn it down to 10-20 RPM and it will operate just fine. As the motor is made to operate at the lower speeds, the problem really comes in not so much with the motor as it is with the air moving capability under static pressure. So if you run every fan, it has a performance curve associated with it. And as we slow this down, its ability to handle higher pressure is lower. So that's really the crucial key. And what we have done is in the Munters Drive themselves, we have programmed in the low speed on the Munters Drive of the minimum where we think it shouldn't go any lower than that.
Okay, well, that's about all the time we have for today. You can forward any additional questions to webinars@annexweb.com and we'll get them answered for you. And another reminder that a recording of this webinar will be emailed 24 hours after the live event. So thanks again for joining us and have a great day.